Gravitational potential energy. There's various forms of potential energy that we're going to be dealing with in this class. And when we talk about potential energy, we mean that there's energy associated with, that's contained or stored in a system by virtue of a position within usually some kind of force field, or something that can apply a force. Like gravity can apply a force. So we're going to talk about the energy stored up in a gravitational field today. If I stretch a rubber band, right, there's energy stored in that stretched rubber band. And that rubber band can apply a force, right? So that's we're going to call that elastic potential energy, and we'll deal with that in a little bit, but not right now. And then next semester we're going to talk about electric fields, and electric fields apply forces to objects that have charge, and we can store energy, or an object could have energy associated with it based on its position in an electric field. So we'll talk about electrical potential energy probably in January or so. But today we're going to talk about gravitational potential energy. Now let's suppose I've got a horizontal surface, and I'm going to put a ramp right here. Here's a little platform at the top of the ramp, and then it just kind of drops off. And right here is a sleeping cat. Okay, so it's all curled up. And so what somebody's going to do is, here's a big crate, okay? All right, and it's on wheels. We'll just leave friction out for a little bit here. And we're going to push this cart up the crate. So here will be an applied force, and we're going to push that crate up the ramp until it gets here. So here's the crate right up here. And then our cruel person will give it just the slightest little nudge. Not a significant amount of energy will be added. Now, I think you can see that the crate has the capacity to make changes to our sleeping cat. Okay, so it has energy because it has the capacity to make something happen. Okay, so now when the crate was down here, it's at the same level as the cat, and it really can't do much to the cat. First of all, the cat is hiding on the other side of the ramp, okay? But also, it's not moving, it's just sitting there. The cat's not moving, just sitting there. There's no energy here. But someone starts to push on it, gets a little bit of velocity, and then we roll it up this ramp. So to get the car, or this crate, up to the top of the ramp, somebody has to do work. Somebody has to transfer energy from their bodies, chemical potential energy stored in their muscles, and, huff and puff, and push it all the way up to the top of this ramp and have it resting up there. So what we're going to do is we're going to look at a free body diagram of this ramp. So you give it a little push. So let's pretend, let's use a little Looney Tunes physics here. You ever watch Looney Tunes? That gravity, look it up on Google or something. Looney Tunes physics. And it has all these laws of physics that apply only in Looney Tunes. One of them is the force of gravity does not take hold until you realize you've walked off the edge of the cliff. And once you realize, then gravity takes a hold, and then gravity acts upon your body before it acts upon your head. So it stretches your neck out, and then you snap your weight. So let's kind of think about that. Let's suppose the crate is right here. Let's not worry about any horizontal velocity. We're just kind of simplifying this. And let's draw a free body diagram of this. Well, it's pretty easy. There's only one force acting on it now. There was a normal force, like here's gravity and here's a normal force. So here's mg and here's a normal force. And they were canceling each other out. Nothing was happening. But now we've got gravity pulling it down like this. Now, one thing I've neglected to do. Let's give this a direction of y. Okay, so here's, we're going to say the origin is right here. We're not going to worry about the x direction here. So this is my y-axis right here. So this is at some initial, we'll call it y initial. Okay, maybe y final is 0 or something. So, or at least whatever the thickness of the cat will be our y final. Now, yes? Well, okay, this is Schrodinger's cat right here. So I'm just trying to get you ready for quantum mechanics when we get there. All right. Actually, you won't get there in this class. But
Schrodinger was a very cruel man.
Schrodinger did not like cats. No, he was a dog guy. That's why we don't have Schrodinger's dog in the box. All right. But anyway, so I think what you can see here is that gravity can do work in this problem. And so how much work can it do? Well, that's what we call gravitational potential energy, is the work that gravity can do. Okay, so the work that gravity can do, no, can do is 2 words. Is called, well, I've written it up here, so I'm just going to put, grav potential energy. And we have a term for it. Like we called kinetic energy, that is the energies that an object has because it has mass and it has motion, it's moving. We call that capital K for kinetic energy. So what should we use for gravitational potential energy? Well, of course we should, but instead we're going to use the capital letter U. Why? Because a whole lot of textbooks use the capital letter U to represent potential energy. At least our textbook does. Different textbooks, I've seen textbooks use the capital letter T for potential energy. I don't know where they came up with that. So every book's different. Sorry, there isn't some committee that's going to decide. Yes?
We wouldn't even put like a subscript like G.
Oh, we're going to put a subscript sub G right there. Yes, you're right. Because there's more than one kind of potential energy. So we'll have a U sub G for gravitational potential energy, a sub E for elastic, and then electric. We'll get to that later. So here's that kind of potential energy. So how much, compared to the ground here, how much potential energy how much potential energy does this have? Well, it's pretty easy. It can do, well, it has a height of y. So, let's do work. Work is equal to, F dot dr. All right, let's get all official about it. Oops. But, okay, look, what is my force here? My force is mg, right? And what direction is mg in? Which we call negative j hat. Do you agree with that? It's in the negative j hat. So let's plug that in here. So we're going to go mg negative j hat. Because I got to be official. Dotted with, now I'm going to, my motion is going to be in the dy direction. So I'm going to say this is just, well, dr can be any displacement, but the displacement is only taking place in the y direction. So I'm going to call it dy. And what direction is dy in? Now, okay, good question. What direction is dy? Actually, the dy's are going to be in the negative j hat direction, but the negative will come later. Watch this. I'm just going to say dy. We'll just say that is in the j direction. But what is my initial y here? We're going to go from y initial to y final. Yes.
I mean, I don't know about this, but like, since we already said that it's y, why do we need to include those vectors? Why couldn't we just say negative mg dy?
We can. We can do that now. I'm going from here to here. I'm being very careful and precise. I always start with my basic definition for work, and then I apply it to the specific problem. Now, you're absolutely correct. Negative j dot j is negative 1, and that negative 1 can come outside. Okay? So the work done by gravity, in this case, is negative. Well, mg is a constant, isn't it? So it comes out of the integral. Now, if we integrate over dy, we're just going to get y from y initial to y final. Okay? But, so let's put the negative, and then we'll put in our final initial here. Negative, and then it's mg y final minus mg y initial. Okay? Well, I got a negative, and then I got a subtraction here. And so I can just switch the order of this if I wanted. The work done by gravity is going to be mg y initial minus mg y final. And these get switched because our gravity is in the negative direction, but we're saying our delta y, our dy, is in the positive direction. Okay, now this works. If I lift it up, look, let's take a look at this guy right here. From here up to here, right? Do you see that we have a positive delta y? When I bring the cart from the bottom up the ramp up to the top, I had a positive delta y. Which means, and since my delta y is up, but my gravity is down, negative work was done by gravity. Does that make sense? When I lifted the crate up, but then when gravity comes down, it does positive work. And you'll see that because if I release this, my y final will be less than my y initial. So this will come out to be positive work. If your y initial is greater than your y final, this comes out to be positive. Well, as a matter of fact, since I'm going to say, let's say the cat is squished to an infinitesimal thickness, we essentially reach the bottom. Even the wheels get crushed. So, bam! I don't know what this is. All right? So sad. This really is a PG-13 lecture, isn't it? All right. Not suitable for younger audiences. Well, if I say that the final position of this is going to be 0, because this is where my origin is, let's make that 0. I can say that, and then y initial, I'm just going to make that y. This is at some height y above my origin. I can say, oh, my gravitational potential energy, U, which is the work that gravity can do if you release it from some height, is equal to mgy. And this is my basic equation for gravitational potential energy. Now you have to understand what you're doing here. When you see this equation, this is the mass, this is the gravitational field, 9.8 newtons per kilogram. If you want to call it meters per second squared, you can. And this is my position from my reference point, from my origin. Is it possible to have negative gravitational potential energy? Yeah, yes, it is. It is. Let me show you an example of that. Suppose, this is my origin right here. Here's my x-axis and here's my y-axis. And notice the x-axis is irrelevant here. And suppose I dig a deep hole. Okay, here's a deep hole in the ground. And Gage has asked one too many questions, so I have thrown him to the bottom of this well. Okay, so there's Gage. Now, Gage now has negative gravitational potential energy, because in order to lift him, the work that gravity will do to get back to my reference, to get back to my origin, to get back to the place where I'm measuring gravitational potential energy from, look, gravity is down, but the displacement, my delta y, will be up. And when the force and the displacement are in opposite direction, negative work is being done. So gravity will do negative work to pull Gage out of that well, if you choose to do so. Okay? Yeah. Sorry.
Do I need to sign a media release or put this on YouTube?
I know. I didn't say your last name. It's Smith. All right. Now, so anyway, this is the equation for gravitational potential energy. Now, when we're working problems, we don't really care about what an object's gravitational potential energy is. What we care is about a change in gravitational potential energy. And later on when we're starting to work problems, like a roller coaster problem, instead of this being a ramp where it falls straight down and we smash some poor helpless animal, which I would never do, by the way.
Would get really magical.
Yeah, I know. This is, it's all about attracting, keeping people awake. Okay, during a physics lecture. Believe me, that's not easy. So if I put a track right here and I made a nice little ramp, okay, I'm eventually going to get to the point where I could figure out what the velocity is at any point on this track by looking at the change in gravitational potential energy. So really what I'm interested in is delta U. Whoops, delta U. A change, am I on screen there? Yeah, change in gravitational potential energy, which is just going to, for most objects, we're going to assume that the mass is constant, and we're going to assume that the gravitational field is constant for now. By the way, when we get to chapter 13, we're going to deal with changes in gravitational potential energy for satellites and spacecraft, where the gravitational field is very much different. It changes with our distance away from the planet, right? You get farther and farther away from Earth, the gravitational field becomes weaker. We're not going to deal with that right now. We're going to assume that we're close enough to the Earth's surface that the gravity field of Earth is a constant. And we're going to deal with situations where the mass of the object isn't changing. The mass is constant. So it's just going to be mg delta y. Okay. Now, one reason I used a ramp right here, this is the last thing I'll talk about. Let me zoom out. Oh, I am zoomed out. All right. Is that Notice as I'm moving up this ramp, right? You can think of this ramp as a change in position. Like here's a delta R, right, from here to here. And delta R has an X component and it has a Y component. So here's delta Y and here's delta X. And notice that the delta X is irrelevant to how much work gravity can do once it gets to the top. What if I made the ramp shallower? Like I started way over here. And so, now my drawing's going to get kind of messy, but oh well. What if I started my ramp over here? And so I had to move my cart up like this. All this does is make it easier to push it up the ramp. But look at my delta Y. It's the same once I get it up to the top. So it didn't matter that I doubled delta X. Delta Y is the same, and that's what determines how much work gravity did getting it up to the top, and that determines how much work gravity can do when it falls back down to the bottom. So, and last thing I meant to mention this, your gravitational potential energy here, mgy, see, y can be negative here, and that's perfectly okay. That is not true for kinetic energy, right? Kinetic energy cannot be negative. You know, we said that kinetic energy equals 1/2 mv squared, period. 1/2 is positive. There's no such thing as negative mass. Now, v squared, what is that? Well, you say, hey, wait, we've had negative velocity before, right? But you square it, what happens to the negative? It becomes positive. And you say, wait, but that negative just means direction, right? Well, what does v squared mean? V squared means, v squared means v dot v. That's what we mean. When you see a vector that's been squared like this, it's the scalar product of the vector with itself, which is the magnitude of v times the magnitude of v times the cosine of the angle between v and v. Well, what is the angle between a vector and itself? 0, which means that this is 1. So that's v squared. Oh, off camera. Nope. All right. So this is always positive. Now, a change in kinetic energy can be negative. You can have a final kinetic energy that's less than your initial kinetic energy, so your change in kinetic energy can be negative, but your kinetic energy itself is always going to be positive or 0. But you can't have negative kinetic energy, but you can have negative potential energy, which is a big deal. Okay, so that is all for this part.